let's start this class with electromagnetic sensing. So, electromagnetic sensing of glucose. Now, in the last class we talked about photoacoustic spectroscopy, and prior to that we talked about thermal emission spectroscopy, and we talked about all the challenges. If you go back, so this is what we talked about, the photoacoustics, where you are using two different kind of radiations or two different kind of waves, and then the use of QCL lasers, and then we talked about how we handle the parameters, then metabolic heat conformation, and prior to that we talked about thermal emission spectroscopy, time of flight and terahertz domain spectroscopy, and prior to that we talked about the far infrared spectroscopy, and before that, of course, in the last week talked about the Raman spectra, right. So, today we will move on to the same line another important aspect of non-invasive glucose sensing, which is electromagnetic sensing of glucose. When we talk about electromagnetism, we all in our, since our standard 6th, 7th, we all have studied about if there is a current flowing through a conductor, it generates a magnetic field around it, and that is the birth of electromagnetism. So, we all have seen that it could be done the reverse way also, which is a dynamo in a cycle and all those things where you are drawing light. So, both these energies, magnetism and electricity, go hand in hand. They are almost brothers or brother sister kind of relationship. So, when we talk about the electromagnetic sensing, it is pretty interesting what we are actually sensing. This technology measures the current or voltage which is proportional to the magnetic coupling between two inductors. Okay. Since the coupling depends on the dielectric characteristics, dielectric nature, this is something you guys again should brush up, of the medium, dielectrics of medium. So, in this case the medium will be nothing but blood between the two coils. It is also proportional to the concentration and type of analyte. So, in this case the analyte what we are concerned is glucose. Okay. Now, in other words, the ratio between the input and the output voltage or between the current is proportional to the concentration of glucose. As I will show you the picture, that will make more sense. Here is the picture. Here is the tissue, here is the blood capillary, here is the skin, and here is the glucose, and here are the inductor coils, primary coil and the secondary coil. Okay, this is the core, and here is the magnet. Now, here what you are doing is the sensor is measuring the voltage or the current depending on the amount of glucose molecule in the capillaries. The concept for measuring glucose concentration in the earlobe using electromagnetic sensing. So, this was done in the earlobe because that is where you have the access to most of the capillaries, because a huge amount of skin area you are getting where it has been tried. That does not mean you cannot do it some other places, but you have to fix the magnet or this device like this. So, there should be a clip. Okay. So, any skin part where you have a clip like this and you have a thin layer of skin where there is a blood vessel happening. So, you can really do it in the earlobe like this. Okay. So, this clip mechanism is needed because here you have the two inductors and there is a magnet out here, right. So, now furthermore, the frequency of the signal plays a fundamental role in to produce enough coupling, although this is also dependent on the temperature of the sample under examination. As a result, frequencies in the band of 2.4 megahertz to 2.9 megahertz are generally accepted to be suitable for detection of glucose. So, for you the take home message is 2.4 to 2.9 megahertz for detection of glucose, variations in vivo, while others such as Meliakan suggested 7.7 megahertz is a better option. So, there are lot of research happening in electromagnetic sensing, because Ear is a easily accessible part. There's a lot of flow of blood and it is easy to do the detection. So, the basic idea is the signal between these inductor coils changes depending on the number of glucose moiety which are present in the vessels. This is the basic fundamental of this technology. Now, next in that line is bioimpedance spectroscopy. Okay. When you talk about impedance, we are talking about some form of obstruction, some form of resistance likewise. Okay. Also known as dielectric impedance spectroscopy. This technology assesses the changes induced by the blood glucose variation in the permittivity and conductivity of the membrane in the red blood cells. So, when we talk about the dielectric, so these terminologies come, permittivity and conductivity. If you look at, as I was mentioning earlier, that you have to see the basic principle of how we measure the dielectric constant, you will come across those words, permittivity and conductivity in the membrane. So, bioimpedance spectroscopy uses the concept that variations in the plasma glucose concentration induce variation in the concentration of sodium and potassium ions, causing changes in the conductivity of RBC membrane, indicating a direct relationship between both. As such, bioimpedance spectroscopy applies a small amount of alternating current of known intensity to measure the associated resistance, as I was mentioning, impedance, resistance, and thus the conductivity. This means the technique is relatively simple, making it potentially affordable and easy to employ in the practical scenario as long as sensitivity to temperature variation and sweat, among other limitations, can be minimized. So, now that brings us to a point under a field condition where you do not have a control on the temperature or the humidity, how you are going to get exact data, because these parameters alters the dielectric properties of the sample or the blood, depending on what is the temperature, what is the moisture level or sweat level, how much, what is the level of sodium, what is the level of potassium. These things will alter. So, bioimpedance spectroscopy, though it is a very straightforward technique, which is dielectric impedance spectroscopy, which is much more scientifically specific name. Dielectric impedance means the resistance what you are measuring in the medium. Basically, the medium in this case is the blood. The way the dielectric properties of the blood changes or the RBC changes depending on the amount of glucose which is present, because RBCs are the glucose carrier, because RBC contains the hemoglobin and where the glucose bind. So, it is basically RBCs are like this, filled with hemoglobin, and each hemoglobin is saturated with oxygen or desaturated depending on is it oxyhemoglobin or carboxyhemoglobin, so on and so forth. Okay. So, next is the use of ultrasound. So, now we are into pressure waves. The technology measures the propagation time of ultrasound waves through the medium. The higher the glucose concentration, the faster the ultrasonic wave propagates through the media, reducing the time of propagation. Depending, because the higher the glucose concentration. So, when we talk about a solid substrate, it is something like this, right, where the sound travels very fast. When you talk about a liquid substrate, it is like this, and when we talk about the gaseous surface, it is something like this. Now, say for example, in this, say for example, this is a liquid, you are increasing the number of glucose moiety. So, what will happen? The sound will travel faster, because in the solid, because if you put your ear on a railway line, you could hear a train coming, because the sound travels, this pressure wave travels very fast in a solid medium, right? If you use that basic concept, what you have studied in class 7, 8, 9 and 10, you can exactly understand what is happening here. That's exactly as the line says, higher the glucose concentration, the faster the ultrasonic wave propagation through the medium, reducing the time of propagation. So, if your capillary has more number of glucose moiety, then ultrasound will travel faster, versus if it has something like this situation. It will take more time. So, Tx versus Ty. So, Ty will be far more less than Tx, and that is exactly is the time what you are measuring here in terms of the propagation of the wave, the time difference. Depending on the strength of the intermolecular bonding forces and the density of the medium, the fluid or tissue has certain degree of compressibility, which determines the acoustics velocity and the frequency waves through the media. As such, changes of the glucose concentration in the extracellular fluid affects the density and the adiabatic compressibility, affecting the acoustic impedance linearly. Okay. So, this is another very interesting way of using ultrasound to measure the glucose concentration. Then comes a technology called sonophoresis. This technology relies in obtaining a sample of the interstitial fluid to measure the glucose by enzymatic method. The difference is that sonophoresis uses low frequency pressure waves to drive glucose molecule out through the skin. It relies on longitudinal nature of ultrasound waves, the direction of propagation being same as the direction of oscillation, to enhance the permeability of the skin and induce phenomena called cavitation. Okay. The working principle of cavitation is not completely well understood, but it consists of a series of compression and expansion movement of sufficient magnitude to extract gas from the tissue, carrying with it other permeant including glucose. So, sonophoresis relies on cavitation. This technology once again relies on obtaining a sample of the interstitial fluid to measure the glucose by enzymatic method. The difference is that the sonophoresis uses low frequency pressure waves to drive glucose molecule out of skin. So, you are basically using low frequency waves to drive the glucose out of the skin. It relies on the longitudinal nature of the ultrasound wave, the direction of propagation being same as the direction of oscillation to enhance the permeability of the skin. So, skin permeability increases, induces a phenomena called cavitation. So, you are completely changing the cavities or the pore size of the skin. So, in a way, you are changing the diffusion potential from the skin by using this process. And since you are changing the diffusion potential, there are glucose molecules which pops out. And that's exactly what sonophoresis does. Ionophoresis, sonophoresis means you are using a sound wave to create a kind of, not say fracture, but a kind of increasing the permeability, or you are allowing something to come out. You are creating pores. Phoresis, you are creating pores. You are using sound to create pores, and through those pores, whatever exceeded out, you are measuring it depending on how much is coming out. So, the technology relies on obtaining a sample of the interstitial fluid to measure the glucose by enzymatic method, but how it does so, the difference is that sonophoresis uses low frequency pressure wave to drive glucose molecule out through the skin. So, in changing the skin permeability and the glucose comes out, it relies on the longitudinal nature of the ultrasound waves, the direction of the propagation being same as the direction of oscillation to enhance permeability of the skin and induce phenomena called cavitation. And as I mentioned, the working principle of cavitation is not completely well understood, but it consists of a series of compression and expansion movement of sufficient magnitude to extract gases from the tissue, carrying with it other permeant like glucose. So cavitation is a very interesting process where something has to come back to its original shape, but it takes time. So for example, expand it takes time to come back to its original shape. During that time, when it is coming back to its original shape, things exuded out. So for example, there's a surface and you're giving a sound wave. So there is a zone where the skin in a microscopic level expand, and then it comes back. But during that time when it expands, there are molecules which are coming out, depending on how much is there. And it's a very indirect way. It's a very interesting way to think through. So this is another technology which is sonophoresis, which is under review. Similarly, as I mentioned, there is something called a reverse ionotophoresis, RI technique. What is reverse ionotophoresis? Is categorized as minimally invasive technology, since it relies on the circulation of a small electric current between an anode and a cathode located in the surface of the skin to get access to a small amount of interstitial fluid. So you have anode and a cathode embedded. So again, these are all part of minimally invasive. In technical textile, you embed these kind of things. The migration of sodium ions primarily produces the current causing convective flow or electroosmotic flow of the interstitial fluid, carrying with its glucose molecules towards the cathode. Okay. At the cathode, there is a standard glucose sensors measuring the glucose concentration directly by enzymatic method. So now you are using, of course, at the cathode, what you are using is the glucose oxidase assay, but you are forcing it. So that's why it is called reverse ionotophoresis. You are basically having an embedded cathode and an anode in your body, something like this. There's a cathode and anode present there, and you are doing the measurement at the cathode. So again, if you go through it, the migration of sodium ions primarily produces current causing the convective flow or electroosmotic flow in the interstitial fluid, carrying with it glucose molecule towards the cathode. At cathode, there is a standard glucose sensor. So this is the whole principle of reverse ionotophoresis. And if you look at how the reverse ionotophoresis works, here you have, there is an embedded anode and a cathode. On the cathode, you have the glucose oxidase. It's amperometric measurement because you're measuring the current. Here you have the reference electrode, here you have the sensing electrode, here you have the reservoirs, okay, where you have the glucose oxidase being immobilized. Now you're giving a small amount of current here. This current actually alters the flow of the interstitial fluid, and this glucose molecule migrates there. So they are embedded on the skin, and some of these glucose gets attracted and moved, and this is the ISF in the interstitial fluid. You have the sodium ions which are moving towards the cathode. You have the chloride ion which are moving towards the anode. So we are creating a potential across it, and there are glucose which along with the sodium is moving there. This is in the capillaries. There is some form of disturbance you are creating, and that's why it is called reverse ionotophoresis. Why it is ionotophoresis? Because it is utilizing the ions, sodium and the chloride, and of course in that process it is measuring the glucose. So interestingly, all these techniques are some way or other, if you realize, you are agitating the skin with, say, a sound wave, you are agitating the capillaries with the anode, then measuring using a cathode, you are agitating the system with some light waves, some laser. So in a way, you are trying to maximize your chances of obtaining a correct set of data. So with all these things, you must be realizing that if these many sensors are there, why are we lacking? Where we are lacking is that we need lot of data to analyze, and of course we need algorithms, and we need very powerful computers to analyze all these different kind of data which are being currently. And these are some of the different technologies which are there. If you go through them, I will just leave it for you guys to go through most of them. There are series of technologies, glucowise, and you can go through. In the Caltech, there's a technology. University of Waterloo, there's a technology. Then you have glucotrack. Then series of them at different places where they have been. Then you have the sugar beet. Then you have the UNIST. Then you have Maryland has a technology. So all this. Then KTH, the Korean Institute, University of Bath has a technology, so on and so forth. There are a series of places where there are a lot of technologies. Tohoku University has another set of technologies. These are the technologies which have been evolved in the university level, who all are into the biosensing for different kind of applications. But as I mentioned in the last class, we are talking primarily of glucose because that is where you can cover the whole range of biosensors for all the biodefense applications, bioterrorist applications, for anything. I mean, this is the kind of sensors available in the market. Now, you have to change the analyte. That's it. Here we are measuring glucose. Instead of glucose, if you could measure something else, that's all. And that is a big challenge, how you could translate it. So it's more to do with, there are a lot of technologies which have been being tested for a simple molecule like glucose. Now, how you translate them is a challenge. So again, to revise, so this is your reverse ionotrophoresis we talk about, where you are using an embedded cathode and an anode out there, and most of the measurements are happening at the cathode. You are injecting a current, and that leads to a mobility of the sodium and the chloride and the glucose which is present, right? Now, prior to that, we talk about the sonophoresis, where it is functioning based on theory of cavitations. We talk about the cavitations, which is very poorly understood phenomena. Prior to that, we talked about the ultrasound, where we said about if the amount of glucose is more in the blood, the wave will travel faster. It's a sound wave, it's a mechanical wave, right? Then we talked about the bioimpedance spectroscopy, which takes into account the dielectric feature or dielectric properties of the blood and of course the RBCs. Then we talked about measuring glucose concentration using electromagnetic sensing, where we had the two inductor coils out there, the core of the magnet, and what are the changes which are happening because of the amount of glucose present. Again, it is using the dielectric of the medium, where you have to go through the permittivity and the other relevant properties of dielectric properties. Prior to that, we talked about photoacoustic spectroscopy, and before that we talked about metabolic heat conformation. Before that, we talked about thermal emission spectroscopy. Prior to that, time of flight and terahertz time domain spectroscopy. Prior to that, we talked about far infrared spectroscopy. Before that, we talked about Raman spectroscopy. Then we talked about mid infrared spectroscopy. Before that, we talked about near infrared spectroscopy. Then we talked about the OCT technology, optical coherence tomography technology. Before that, we talked about optical polarimetry. Before that, we talked about FRET, fluorescence resonance energy transfer, and fluorescence technique in glucose monitoring. So overall, if you look at it, and before that we talked about SPR, and these are the different level of detection, and before that we talked about all the in vitro technique, and here we talked about all the non-invasive in vivo technique. So with this, I will kind of close this part of glucose sensing to give you an overall picture that what all technological advancement which has happened. I believe by this time you people are well versed of the technologies which are available across the world for you to explore, read more, and realize that sky's the limit. Whatsoever technology you pick up, you really can do wonderful work in this area. It's just opening up, and there will be a lot of work which will happen on flexible electronics or biosensors, then technical textile integration of biosensors for all kind of applications, from civilian application to strategic application to application in Army, Navy, and Air Force, and especially in the bioterrorism. And apart from it, there will be a lot of scope for people who are into data mining and data analysis and optimization algorithms for central data sensing platform, and specifically in the warfare zones where centrally located data mining will be very critical for the future well-being of the soldiers. So I will close in here, leaving you people to dream of a future which will have tons of such sensor embedded in our dress, in our fabrics, and it will be a very different world. We'll be able to predict disease, or we'll be able to predict pathogen, we'll be able to predict situations which could lead to heart attacks, right? So once again, thank you. So we'll catch up in the next class with more of these stories of sensors and how it is changing the growth of human race. Thank you.